Okay, guys, so section 4.5 is all about solving exponential equations. 4.6 we'll be able to get into the application, but right now I just want to solve these. And it's not just exponential equations, we're also going to be solving logarithmic equations. So I want to show you a few of the different types that you'll see. Okay, so let's start with this. 5 to the x is equal to 13. Now, the way we solved these before is we tried to get a common base, right? And then we would say, okay, if the bases are equal and these two expressions are equal, then the exponents would have to be equal. But it's not so easy to get common bases in this case. So what can I do? Well, I'm going to use properties of logarithms. So what I'm going to do is I can take a certain log of each side. I can choose any type. Usually we use natural logs. So you should be able to convince yourself that it's fine to take the natural log as long as you do it to both sides. Now, if you remember, there's a property of natural logs that says I can take this x and swing it out front, right? I think it's the third property in that green box. So that's what I'll do. X times the natural log of 5 is equal to the natural log of 13. Now, the important thing to realize here is natural log 5 and natural log 13, those are just numbers, some decimal answers that you can type into your calculator. So these are just like regular numbers. So if I want to get x by itself and it's being multiplied by natural log 5, that number, then I simply have to divide both sides by the natural log of 5. I do that, and I get an exact answer for x, the natural log of 13 over the natural log of 5. Now that would be fine. That right there is what we call our exact answer. Okay? If you like, and depending on how the question is phrased, you can give an answer rounded to the nearest thousandth. So if you type this into your calculator and you round it off, that's about the same as 1.594. Of course, that's important in application, so you can see, well, what is that number? But exact answers are always more exact, so that's the advantage there. Let's look at b. b works very similarly. We have 1/3 raised to the x power. So let's go through and I say, okay, well, I can once again take natural logs of both sides. You don't have to take natural logs. I could do log base 10s. I could even do log base 1/3 or log base 6. I just like to stick with the natural logs myself. I'll use that same property, so I'm right here. And then finally, it's the same thing to get x. X is equal to the natural log of 6 over the natural log of 1/3. Okay. Now you may see in the book, sometimes they go here and they'll write it a little bit differently. Okay. So that would be the same as, you could see something like this, the natural log base 1/3 of 6. That's just using, if we go to this is just a reverse change of base. Okay. So you could see it like this. Just be aware that these are the same thing. I, of course, prefer this form. Okay. But you could write it in this form as well. C, 2 to the x plus 3 equals 5 to the 2x. Once again, no common base. So I'll take my natural logs. Don't worry, I promise we'll get to some more interesting problems here in the next one. So I took natural logs. I'll do the same thing. Remember to put that in parentheses because it's that whole x plus 3 being multiplied by the base there. And over here, I get a 2x natural log 5. Okay. Then let's see what we got. Well, it looks like we have x natural log 2 plus 3 natural log 2 equals 2x natural log 5. Now, like I said before, don't get intimidated by all these natural logs. These are just numbers. So how do I get x? Well, I should probably get them on the same side of the equation. So I'll do this. That's going to leave me with 3 natural log of 2 is equal to 2x natural log 5 minus x natural log 2. Okay, well, I got two terms with an x. I can't really just subtract them because one has a natural log 5, one has a natural log 2. So what the heck am I supposed to do? Well, what if I factored out an x? Like so. See that? And then I can divide it out. That means x is going to be equal to 3 natural log 2 over 2 natural log 5 minus natural log of 2. There's my nice exact answer. Now, it's important to remember you can check these, okay? You are able to check these. So be aware of that. Sometimes it's a little bit of a pain in the butt, but you can do it, okay? Let's move to D. E to the 1 minus 3x times e to the 5x equals 2e. A little bit different. But if you haven't noticed, in all of these, it's always one base with possibly an exponent is equal to another one, okay? Let's do that. I could combine these into a single base of e if I add the exponents. I think that might be helpful to us. Then that leaves me with e to the 1 plus 2x equals 2e. Now there's different options here. You could take natural logs and expand the right-hand side. What I think is easier to realize is notice e to the 1 plus 2x is the same as e times e to the 2x. Technically, this is e to the 1. See how I used the reverse rule. So here, I was able to add exponents and combine them into 1. But instead, what I did here is instead of adding, I split it. So I kind of did the reverse. But why did I do that? Well, look, both sides have an e. Why don't we just divide both sides by e? Now e to the 2x equals 2, and that's fairly easy to solve. Take your natural logs of both sides, like so. Swing that 2x out front. Realize that natural log of e is really just equal to 1. So then all I have to do is divide both sides by 2, and I get x equals natural log 2 over 2 for my nice exact answer, which, in case you're wondering, is about 0.347 when rounded off to the nearest thousandth. I want to look at this one now. This one's pretty interesting. 3 to the 2x minus 12 times 3 to the x equals negative 35. Looks a little intimidating. I want to write it like this. And what I want you to notice here is that both of these two terms here have this same base of 3. And here's what we're going to do. Notice how there's 3 terms. Pretend that instead of a 3 to the x and a 3 to the 2x that I had an x squared and an x. That would just be a quadratic. We would know how to solve that. Well, I want to show you that we could write this like this. See 3 to the 2x? Make sure you can convince yourself that that's the same as 3 to the x squared. Once again, I'm using kind of a backwards property from algebra. Usually, if we have something to a power, we multiply the powers. I just use the reverse. Well, why did I do that? Well, take a good look at this, okay? And if 3 to the x was just, say, an x, let's say it was the letter u, then this would just simply be a quadratic equation. So what I'm going to do is I'm going to do a substitution. It's called a u substitution. I'm going to let u be 3 to the x. In that case, u squared is 3 to the x squared, which u and u squared, that's what I have here and here. So what I have here is I have u squared minus 12u plus 35 equals 0. And all of a sudden, this looks a lot nicer. It looks like something I can handle. Okay. Now, we're going to solve for u, but then we're going to re-plug in what u is to get x. So I believe this factors as, let's see, a u, we have a u. How about a minus 7 and a minus 5? Okay. So I can see, okay, well, here we get u equal to 7. Here we get u equal to 5. But we don't want what u is. We want what x is. So for u equal to 7, I have 3 to the x equals 7. This I know how to solve if I take natural logs of both sides and I swing the x out front, then I'm going to get x equals natural log 7 divided by natural log 3. That's one of the possibilities. And if u is equal to 5, likewise, 3 to the x is equal to 5. Take your natural logs, swing the x out front, x equals natural log 5 over natural log of 3. That's your other solution for x. Okay? So these are the different types of exponential equations that I wanted to show you. Next video will be some logarithmic equations.